Hello and welcome to Hot in Math. In this edition of Hot in Math, we're going to talk about algebraic representation of vectors. So the goal is here for you to use coordinates to perform vector operations. All right, so we had talked about the form of a vector and its direction and magnitude. And previously, we were talking about geometric representation. I gave you the component form but didn't highlight it as the math language that is described as component form. So the direction vector v in this case is going to be -3, 4, and we call that direction vector and the form of that direction vector in parentheses component form. So -3 describes the direction in the negative x direction, the negative x-axis, and then +4 in the positive vertical or y direction. So the vector is represented as the red vector, moving 3 units to the left and then 4 units up. And that form in parentheses, like a coordinate, is called component form. But instead of a coordinate, it's giving you the direction, and then ultimately you can derive the magnitude from that vector. All right, so what I want you to do is I want you to see if you can use trigonometry to find the coordinate form of a vector. So we're going to back into the coordinate form. Understanding the magnitude of the vector in red is 15 newtons, and it's at an angle of 70 degrees with the positive x-axis. So what I want you to do is to find F, the force, in component form. So I've given it to you in magnitude, and also I've identified the general direction by giving you an angle measure. So let's see if you can find the component form of this vector. I'm going to pause here. All right, so this is a simple trig problem. I know if I label the opposite side as y and the adjacent side as x, I can rewrite the xy change, or the component form of the vector, as y comma x, or x comma y, excuse me, with y being equal to r, which is the force, the magnitude of the vector, times sine of 70, and x is equal to r cosine 70. So as we set this up in an equation, we can see that y is equal to 15 sine 70 and x is equal to 15 sine 70. And when we calculate that, you come up with the force F as a component in component form for that vector as 5.1 comma 14.1. All right, so the magnitude is what I've given you previously in the example. Magnitude just establishes the length of the vector. It doesn't define its direction. So the magnitude is in the absolute value brackets. So I take the vector, apply the absolute value brackets, and then that tells me that I need the magnitude or length of the vector. And you can figure that out by using the distance formula. So in this case, it would be 5 minus 2 squared plus 6 minus 2 squared, and then taking the square root of that summed value. So 5 minus 2 squared is 9. 6 minus 2 squared is 16. 9 plus 16 is 25. Square root of 25 is 5. And that ends up being the length or the magnitude of the vector. So again, you can use the distance formula to find the magnitude. All right, so there is the work. All right, so we did this problem, so we're going to skip through this. And by the way, the magnitude is 15. I'm just kind of asking the problem in a different way, but just asking you to realize that typically newtons and force represents the magnitude. All right, so vector operations, vector addition. If I'm adding two vectors together, I'm just adding in component form the x values together and the y values together. So if I had the two vectors v plus u, and v is ab and u is cd, then simply v plus u is a plus c, comma, b plus d in parentheses. If I subtract v minus u, and so we said, again, minus u is just the vector u that moves in the opposite direction but with the same magnitude. So it'd be a, b for v, and c, d for u. Subtracting those, I get a minus c, then comma b minus d as my component form for the subtracted vector sum. Scalar multiplication we talked about. I can multiply any vector by a given scalar or multiple, which can also be a fraction or a value between 0 and 1, and also can be a negative value. So k in this case I'm going to make is 2. 2v ends up being 2 times a comma 2 times b. Or in this example with k as any vector, kv is equal to ka times kb. All right, so I want you to perform these vector operations using the values here. I'll come back in a minute. All right, so v plus u is equal to 3 plus a minus 1 comma 2 plus 4, 2, 6. V minus u is 3 minus a minus 1 comma 2 minus 4, or 4, negative 2. And 2v, I've multiplied v by 2, so 6, 4 minus 3u, negative 3, 12, ends up being 6 minus a minus 3, which is 9, and 4 minus 12, which is negative 8. All right, I want you to find the values for these, perform these vector operations on these vectors. I'm going to stop here. All right, you see that v plus w is negative 8 plus negative 6, comma 4 plus negative 2, or negative 14, 2. 2 times v plus w. So we said the distributive property also applies to vectors. So this ends up being 2 times negative 14, 2, which is v plus w, or negative 28, 4. And then 2v plus 2w, believe it or not, ends up being also the same as 2 times the quantity of v plus w, as we mentioned, distributive property holding in vector operations. So 2 times v, negative 16, 8, plus negative 12, negative 4, leaves us with negative 28, 4 as our resultant vector sum. Right, that's it for algebraic representation of vectors in this edition of Otten Math. Please join us next time when we continue to talk vectors in our next edition in 12.3.